Meanwhile, time is coming. So today, Yanis will outline the solutions of the second package of homework. I hope you had time to look at problem formulations, perhaps just, try to figure out what are the steps, what do you miss. Let's see, let me formulate it more precise terms. You look at formulation, you kind of make a plan, how would you do this problem? And you might, in this process, you might find some deficiencies, like you don't know what to do, you don't know what are the steps, or you miss some information from the course, which would permit you to understand how to solve the problem. Right. Although it's kind of events of your personal life, I suggest you kind of also ask questions like this during the presentation of Yanis, kind of trying to understand how this problem fits into the course. Right, with this I will slowly switch to Yanis. I will stop my share, and I actually need to enable sharing, and I would like to put Yanis into sports. Yes. Good. Yanis, the floor is yours. Very good. We will see. We see. This I see your application window. Transmission distribution from current. Okay. So please.
So hello everyone. Today we are going to consider 4 exercises to overuse them all. So the first exercise is going to be about getting the transmission distribution of the current, and this we are going to use a formula which is given in the book, for which is derived from the quantum circuit theory and in a rather complex fashion, but it's a simple formula, and we want to invert it, and this is going to be our main task on this first exercise. The second exercise is, in the second exercise we are going to use this formula to see so it's one thing to have a mathematical formula. The other thing is actually to apply it for a particular situation, and that's what we are going to do in the second exercise and consider actually a system consisting of 2 parts. One is a diffusive connector, and the other one is ballistic one, and see how the compound system, what's transmission distribution, what's transmission distribution of the compound system. The third exercise is going to be understanding single electron transistor. This is going to include column blockade, and these are basic element master equation, and these are basic things one needs to master, for example, to go to this exam. And this fourth exercise also is about the master equation and column blockade and usual stuff. So let's go to the first exercise, transmission distribution from current. So what we have is we shall draw it. We have let me put it. Okay, so we have a diffuser connector and we have a ballistic one in series. The question is, so putting some voltage in between, what would be, for example, this what is the transmission distribution, this row of component system? Oh, sorry. So this is the second exercise. This exercise is about, so we have this formula. We assume that it is given, and we see we have I of phi, where phi is a kind of a phase. It's not a superconductor phase. It's a different kind of a phase introduced mathematically, and its purpose is to. So we know that if we have two elements in series, for example, as here, let's say we have phi. I cannot write it. Phi and theta. Then in the series, we know that if we would consider it as a single element, some black box, then its phase would be phi plus theta. So, and that's a very useful property. So one can consider multiple elements in series or different kind of things. And all right, we have this formula. It has transmission eigenvalue here. It has this phase here, and the denominator sine square phi over 2. And yeah, that's basically it. And we want to know how to get this one. How can we get this? And yeah, let's then proceed. So it's the steps. There are four steps in this exercise, and let's do them faithfully. Until the end, we're going to get the formula. So the first task of this exercise is to make a substitution. So what we have is, the task says that we have to substitute z is 1 over sine square phi over 2. So that means we can put z square, 1 over z square here. So this we already know that it's 1 over z square. And for sine phi, what we do is we say that sine phi is 2 sine phi over 2 cosine phi over 2. And cosine phi over 2 we can express again as a sine square 1 minus sine square phi over 2. So the sine is kind of when we take the square root, it's well, one needs to be cautious what one does. But in this case, the square root needs to be positive because we want the current to be positive. And when we substitute these formulas inside, we get this one. And right, that's the first task. And let's proceed for derivation. The next thing is that one needs to consider, let's promote this z to be a complex. And this complex is such that it's z is t prime. Let's put it at t prime so we don't get confused. plus I epsilon, where epsilon is going to be a small quantity. So we set its set is x by x. Z is yeah. So we start with this formula, and we set z yeah x meaning that's t prime, and we plug it in this formula. And why we want to plug it in is because we know a following thing, that if we integrate, if we are integrating, oh, let's call it, this is real z and this is imaginary z. If we are integrating some function over real x-axis, and we are putting in a singularity, which is happens to be t prime plus I epsilon, then what one can do is to get away from this singularity is one can actually write it in a form where you have the singularity in between, and between, when this singularity is between, you integrate around it. And this is a meaning of this formula. So this part, these two symmetrical cuts, is a Cauchy integral, and this I pi phi x at x0 is this singularity. And what is nice about this formula is that you can separate, when you say that you want only imaginary part of this formula, you don't actually need to compute the principal part of the integral. And that's going to simplify a lot of stuff for us. So we substitute the z inside, and right, so we substitute it in. Let's see if we are not confused. Yeah, the x is this t, x is t prime. It was put in there for not to confuse ourselves. And we see when we substitute this z is t prime plus I epsilon, we get this following form: the real part, and the complex part. Now we say that we only want, so since we have imaginary part already here, which did come from, yeah, which did come from here, then we just take, see, imaginary times imaginary means that it's real. So we take the real part of the full equation, and we get a formula which is fairly close to what we want. And this is a yeah. So this is a second task, and now we need to proceed to express phi as function of what? Of t, I guess. So we introduce the substitution without any justification at the beginning, and what we're going to do is we want to get the inverse. So the simple thing is, what to do is we say that sine phi over 2 is 1 over square root of z. That's what one always can do. And one would naively what would do is say that phi is arc sine of 1/2 square root of z. However, yeah, that's what that naively does. But the arcsinus of complex z, you actually, what we want is we want to, so it's since z is complex, so we want to get rid of the complex part of this. When we want to have formula, we don't want to evaluate it on the complex plane. We want to evaluate on the real plane. So that's not good enough. So we say that we use a formula for complex arcsine of z, and this formula can be derived. So you see, it's very kind of quadratic, like solution to a quadratic equation, because it is actually a solution to a quadratic equation for and a logarithm. And that is nice, but we also know that we see that there is this complex I in here, but we don't want to, we want Z to be kind of, don't want it to be complex. So we use a formula for arccosine Z, and that allows to express phi of Z. I see a question. It's a question from Royal. Can you please tell me which slide? I didn't see. 159. Substitution. For x to t. Okay, this one probably. Are you confused with this part? Okay. So a little bit of so there is a bit confusion. There is the 1t which is integration here, and there is and we want to, as you will see, we want to actually substitute this z with t, but for the derivation it's better not to substitute with t, but to choose a different name for this t, and it's chosen to be x. I think this is actually x, yeah, because it's rho of x. So why do we substitute? So we want to apply this particular formula, and this particular formula, to use it, we need to have something which is singular, x0 here, right? Okay. So it's probably the integration was confusing. Okay. Yeah, typos are present. So yeah, ask questions. So I could eventually correct them. Okay. Right. So so we are now at the position to get. So we derive this formula for rho of t, but we need to find the phi of z, phi of t, and right. So we can actually do it. So this formula for phi of z, and now we can evaluate phi of t. So for as many complex functions, there are multiple branches present, and what I meant with this. So we want to evaluate phi when z is t. And so we have this formula, and what we want is z is t. It's okay. So when we plug it in, so we plug it in here, and we get that we can have a formula as follows. And now we finally can say that we have the solution. So the rho of t is 1 over 2 p g q t, 1 minus t, real part of I of phi of t, where phi of t is pi minus t 2I r cosine of 1 over square root of t. So this is a solution to this exercise. Right, so it's time for your questions. Do you have one? It's maybe the complex analysis always taking square root is always confusing. Was it clear? Yeah, so we have 5 minutes. Let's have a 5-minute break until 12:15. And I think to think about so let's phi of t. Okay, so so we have phi of z, right? So this is what defines z as function of phi. No, it's not complex. So the complex. This exercise is more like showing how to the foundations, how one formula follows from another one. I would say that if you haven't done complex analysis, it's also good to see if you wish to, like you are exposed before your knowledge of complex analysis to this exercise, to this method, and now you maybe become more passionate about the complex analysis you decide to take the course, but it's not going. This particular problem not going to be to exam. So how we got phi of t? So we know that z, we define z in actually the first first task for the substitution. And now we want to invert it as, so this we want to get phi of z, right? This gives this a phi of z. Previously, what we wanted to know that the phi is, we need that the phi is function of t of so the phi is function of z, and we want that the argument of this function is t plus I epsilon, and that's because yeah. So we derive not the function as I of phi, but we actually derived it as, why did I write it? We derived it as z. And we know that z is function of phi. And so this is also, sorry, it's a z as function of phi, more accurately. And so no, it's, sorry, it's phi. This is set. This is set of phi. Yeah, one can get quite confused with this exercise. I hope that you would try to look in the slides and try to yeah, try to go the reasoning again. The question, how we got phi of t? So we introduce the t. So in one way to answer it is so we have this integral and the x. So we change the integration from to the variable of x, and here we substitute this t. We know this t is in between from 0 to 1, so it hits singularity. And it happens to be so that it enforces what x is here. So it becomes t here for the singularity. And yeah, and so Yeah, and then we need to take this real part of current as which is a function of z. But we want to put the z back. We want to put z its corresponding value, which we know is t. So we know that phi is kind of a t. No, sorry, not phi is t, but we know that the z is t. This is t. And we want to know for what phi it corresponds for the current, because the current is function of the current is function of phase. Okay. Oh, I see you answered. So, all right. So yeah, time had passed. Let's move it on the. Okay, so let's have a 2-minute break, and you might think on this particular issue that, for example, we can. But what if we would put the, for a singularity from the top, not from the bottom, or what if we had considered the complex phi, the complex conjugate of phi instead of phi? So let me be back a minute. Okay, let's work on the second exercise. 2B. Since it did take a lot of time, let's do the following. So I will give you the explanation for the exercise, and then let's have a you post the questions. I will see that you have, but let's answer. Let's answer them after the explanation. So the second exercise is about using the formula we obtained in the first exercise. And so in this exercise, what we have is following. We have a diffuser connector, and we have a ballistic connector. And on each of them, there is some phase drop. For ballistic connector, we're going to have, for diffuser connector, we say that the phase drop is theta. And for diffuser connector, we say that not for ballistic, say it's phi minus theta. So the full phase drop of the system is phi. And the question is, what would be? So there are multiple questions in this exercise. For example, what would be the transmission distribution of this full system, and what would be the Fanov vector? So we know this formula for the current. And previous exercise we showed that the transmission distribution can be obtained from the formula above. And right, and then we're going to use it for Fanov vector, which can be expressed from the transmission eigenvalues alone. Right. So the first task is that we need to show that we can get formulas for ballistic and diffusive connector. And so we have two different limits. In diffusive connector, it's known that the phase drop goes to zero. It goes to zero. Well, it goes to zero. And in such case, we can substitute this. If it goes to zero, we can get substitute sine phi to phi. Also, the sine square becomes kind of a zero in comparison to 1. And we get the following formula. Get a formula as follows. This should be theta. And sine theta is theta, and we define this part as a conductance of diffusive connector. The second thing is ballistic connector. Ballistic connector is when it's completely transparent. So T goes to 1, and if it goes to 1, so we have this particular formula. It happens to be so that sine phi is so this is 2 sine phi cosine phi over 2, and again we know that this one would be cosine square phi over 2. So and then we get a tangent plus some integral of rho of the transmission distribution times quantum conductance. So that was the first task. The second is interesting. So we have this. So as I said, we have this diffusive connector and ballistic connector in series. We now want to know what would be the compound system. And we ask the question: what it would be the phase dependence of the compound system? We know that the current is conserved, so it goes from one element, then it goes to the second element, and we know that the following equality holds: that ballistic connector is equal to diffusive connector, where theta is dropped on the one and the phi is on the other one. We obtain the formulas for ballistic and diffusive connector, and so we get an equation that's pretty nice. But it's transcendent. We cannot meaningfully solve it. Fortunately, it's possible to say that consider each part of the equation separately. What we have is, let's write it accurately. we have two GB GD tangents x, where x is let's say x is this quantity. Let's denote it by x is phi minus 2x. So let's draw. We know that how tangents looks, and we know how the linear function looks. So let's draw it as function of each of these equality at x. So we have a tangent which goes to infinity of pi over 2, and we have linear function which goes downward. And it happens to be that the crossing is actually theta. So this is theta, and so what we see is that the coefficient in front of the tangents, if it's small, getting smaller and smaller, or tangents getting less and less, with less and less slope. But anyway, it goes to infinity at some point. So it shows that the phi goes to 0 when GD over GB is going to infinity. Sorry, it goes to 0. And that's what this exercise asked for us. The third question is demonstrate that the diffuser connector actually becomes relevant. And we again can draw a picture. Let's draw only this part of the tangents. Yeah, look like tangents and pi over 2. And we have what this would go from pi. I guess. Yeah. Let's assume it goes from pi and then it goes from, downward like this. Now we see it's the theta is looks kind of more important, and the question whether it goes to 0 or it's at this particular limit or it goes to infinity. So we take the equation. We know how ballistic equation for how the current for ballistic connector looks like. So, and we know that theta is small. Let's see what happens if we expand it in Taylor series. So we say, oh, the current of as function of phase is total, is ballistic connector as function of phase minus theta, where we say that, let's see, if we expand it, ballistic connector as function of phi minus theta over cosine square of phi over 2, which is derivative of tangents. And we see if phi is pi, the cosine of pi over 2 goes to 0, and this thing correction blows up. It blows up. So the perturbation theory wouldn't work here. And
Yanis, there is a question in the chat.
oh, okay. I think it goes. This question is it's 1228. Ah, okay. This is just us to integrate over other t values. Yes. So. Well, we still integrate over t. Typo of mine. That we just define. We define conductance of diffuser connector GQ 0 of 1, rho of t dt, but we actually don't know what it is. So we know that it's just is a number, and since it's a number, let's give it a name, and we now give it the name of GD. So does it explain? Does it answer to your question at all? Okay, great. Right. So we got to the point that our collection blows up. So let's do better and actually do a better interpretation theory, basically. So we consider the limit when phi is pi. So what we can do is say phi is pi minus delta phi. Then tangents of phi over 2, I guess it was like that, is becoming, for example, 1 over, so it's cotangents. It's first is cotangents, delta phi over 2, and then it becomes 1 over tangents phi over 2. And that's much better in a sense that delta phi, we know that this delta phi at this particular limit is going to 0, so we know how to expand tangents. I mean, so we say it's 2 over delta phi. And that's basically what's being done here. We have this pi, and cotangents is becoming 1 over tangents, and tangents is expanded in series under the denominator. Right. Now we know how to express ballistic connector as function of phi and theta at this particular interest region. We can equal them to get theta. And when we do so, we get for a following formula. And it follows that we know in the theta, then the current follows when we put the theta in the formula for this fusing connector. And this is kind of this actually, yeah, wait. Is it? Oh, it's not the end of the exercise. So right. So this gave us the current of diffusive connector as function of, so the full current as function of phase. But what we want is we want so this is I think the numeration is incorrect. So this answers to the third task. Let's now go to the fourth task, which is, now we know how to get phi. We know current as function of phase. Now let's focus on how to get transmission eigenvalues of this characteristic dependence. Right, so we now going to apply this formula. And first we do First, if we want, we could plug in a diffuser connector here. We'll get distribution for diffuser connector. If you will plug in yeah, if you would plug in this one, then it would kind of follow, since it doesn't have any complex part. That's a distribution function would be 0, but it's certainly not the case. And this is kind of a peculiarity. One always needs to think about what happens at the endpoints of the integration. And so our previous derivation, which we did, so this formula, it holds only for what it holds only. So this derivation which we did hold only for limit when t is from 0 to 1. But for ballistic connector, we know that t is 1, so it's kind of not considered, and one needs to consider do a separate consideration. But we know that it will be some delta function. One could represent it as delta distribution at t minus 1, for example, at 1. So that's it, and let's now do the hard part of plugging in the phi in our formula. And it's actually not so hard. So we know that this is the current for this combined system. And we now need to substitute this formula inside here and take the real part. It also doesn't seem, sorry, we not substitute, we it's actually opposite, so let's not confuse ourselves. So this is a function of current as function of phase. The phase is here. We obtain the current as function of phase here, and we know that for the particular phase, we need to substitute this quantity inside, and also it inside here. When we substitute it, we get that the transmission distribution for rho of t is r cosine gb over gd minus r cosine of t minus 1/2. And one can do some magical Taylor expansion and make it more concrete at the limit when gd is what is limit of this thing? So this thing is like a kind of a peak. So this r cosine 1/z is a function kind of this peak, and then one can substitute some different function with a peak, and you get some similar result. So that's I guess this is answer to the task 4. And now we are positioned to evaluate the Fanon factor. Again, we can consider Fanon factor for diffusing connector. And to do so, we see in previous problem solving session, we obtained the formula for Fanon factor as function of transmission eigenvalues. Now we have a transmission distribution. So we need to change the sum by integral and introduce this distribution function, and that's basically it. And we know the distribution function for diffusing connector. One substitute it and gets that Fanon factor for diffuser connector is 1/3. And for ballistic connector, Fanon factor is 0 because all t's are 1. So this thing becomes, this thing cancels. And now if you under the combined system, it's 2 GB over GD, and we shall now analyze it, not analyze it, but see if GD is very large, the diffuser connector is very large, we get to the limit of a single ballistic connector. But if on the other limit is GB is larger than GD, and the previous derivation then doesn't hold, but then we know that the Fanon vector is 1/3. So it kind of shows where this shows how well at what range of GB and GD ratio or derivation is valid. So that's it for this second exercise. So, yeah. So you should now let's ask me a questions and see. Yeah, let's see. How do you get 1/3 out of the integrals? I guess you put it. I would put this integral in mathematics and don't worry about it. But if you want to actually integrate it, then you say that you make a substitution. T is a trigonometric function. It's a square, I guess. Yeah. Yeah, it's one evaluates it numerically, for example, and gets 1/3. But if you show me that it doesn't evaluate 1/3, then we might discuss if it's correct one. Does it kind of okay? This doesn't answer your question, but does it satisfy you? Well, does this explanation satisfy that it's 1/3 because it numerically is so? Okay. Okay, let's have a 5-minute break for you to look into what you have done. So you can look into whether you have more questions. So I think that we shall proceed on the next exercise. And the next exercise is to say that it's very frequently, a form of it frequently appears on the exams, so it's kind of a easy exercise which we can modify to make an exam for, and it also contains a lot of quantum transport stuff. So, right, single electron transistor. So what it is? Fortunately, we have a picture. I didn't want to draw it. So we have a following system. We have capacitance CG. We have an island, and this what's important that this island can't have some n electrons in it. And this island is separated by two, I guess, two weak. It's kind of two tunnel junctions, I guess, how you say it. And tunnel junctions have conductance, and they have also some capacitance. And the question is, what would be how the IV diagram would look like? So we change the gate voltage. One can change the gate voltage. One can change the bias, V right minus V left, and one wants to know which region, for example, is conducting and which not conducting. Let's say conducting, non-conducting. But we already know that there are going to be some non-conducting regions which are column diamonds. And let's now go through explanation why there are these non-conducting regions. So for this particular system, one knows that one can derive and that electrical energy is given in the following form, where there are n electrons on the island, minus Q over E, where Q is the charge screen on the capacitor, which is as a function of the gate voltage and other quantities. And right, so we want to understand the column diamonds, and to do so, what we are looking for non-conducting regions. So the delta energy for example, so we are considering the processes, and the processes changes the number of electrons in the island. We want to know such a process where it's not possible to change number of electrons in the island. And so that would mean that delta energy for electron to hop from the left to the island. So let's say we have center electron, and this is a hop from the left. Energy difference, that means we need to take off also we need to work add work that we take the electron off where it likes to sit in. So we subtract minus EV left, and electron which should hop from the island to the left. We also don't want to have this process, and in such case we would get some help of the quantity of EV left, and the same applies for the hop to the right. FR means from the right, so it's an opposite arrow, sorry. And this means it's hop to the right. So that's what it inequality says. And it turns out that when we express this E electric, the difference of electric energies, we get this combination Q over E minus N, and this particularly shows that we are safe. It's a kind of a periodic. It's a periodic function in terms of. It's going to be a periodic function in terms of Q, and that's why we can pick this N0 for the moment, for the simplicity. And right, and in this exercise, in this task, we are asked to determine the shape of the column diamond. And for the case when we have an asymmetric voltage bias, V left is 0 and V right is V. So electrons are flowing from the left to the right, to the positive. Right. So we write these energy differences. We can write them as follows. And the important stuff now is to draw them. To see the diamond. This is more complex thing. So when I draw them, let's see. Oh, some space here. So if we start with this particularly the simple first equation, which is we see. We start with this equation, then I come to the point that it corresponds to a line, not a line, but the boundary corresponds to a line where number 2C, right, which connects them. And the larger than one, the inequality corresponds to this side of the region. Similarly, the second equation corresponds to minus E over 2CG, and it corresponds to this side of the line. And then we have 3 and 4. Which corresponds to this part, the inside part. So again, this one corresponds to 1. This corresponds to the 2. These 2 corresponds to the third and fourth. And this point, so I draw it asymmetric for a reason, because this particular point is what it is. Like, let me just write it up. Let's call it V0. Sorry, it's a messy. So I was drawing this in VG and B plane. And let's call this point V0. V0 is 2C right over E plus E over EC minus 1. So it's smaller than this lower point. And this one needs to keep in mind that if you, well, it's usually you see symmetric bias, and that's why our column diamonds look nice and symmetric in some pictures on the walls or in the books. But if you have an asymmetric bias, then you need to take into account that the picture also changes. So not the picture changes, but the look on the picture changes. Yeah, so it's something to be aware of it. Right, so that explains. So this region is non-conducting because it's all delta E's for these processes are larger for 1, larger than 0. Sorry. Now let's consider single electron transfer, and for single electron transfer we need to consider 8 inequalities, but it's not so bad. So what we actually can do for simplicity, we know the column diamonds where they were. So this is a gate voltage, this is voltage, this is our column diamond, and we can draw. We know that the column diamonds are periodic, because as I explained before. Does it look symmetric? Okay. Right, so, and now we have these lines, and each line corresponds to an equation. So this is this way. Oh, yeah. Corresponds to this line, corresponds to this thing. Right. This is the column blockade for n is 1, and this is column blockade for n is 0. Now we need to relax this particular relation. Not to relax, but invert it. We need to find edges, edge of it, and invert it. The edge of this one is, I guess, not I guess, but it is the top one. also here. So this corresponds to, let's call it A, and B. This inversion corresponds to A. Oh, I cannot understand anything of it. Let's go to the color, better one. So this corresponds to inversion A. The second one is inversion of this, and its edge is it is actually not like the second one. So it corresponds to inversion of this edge. So, well, the other quantities needs to be the same. That means that this particular region is the process where we have a single electron transfer. So one doesn't need to draw all the lines, but we need to understand where these the inequalities come from. So one starts with column diamonds and then shifts them depending on the number of electrons, and then when we have a fixture, then identifies from which edge you want actually transfer to happen. And how we do get inequalities for n is 1. So beginning of the exercise, so we say that we are considering that in all processes where electron goes from where electron enters the island or leaves the island. So there are 4 processes because we have 2 arms, and it's independent of a number of electrons. Now, particularly interested in the process where we have only at maximum we have can only have a single electron on the island. So yeah, so it's the same, the formula on the first the slide, and we just substitute n is 1. One substitutes n is 1 and gets a column diamond or gets these inequalities, where important one is that we need to invert this particular inequality, meaning which is, let's see the order, actually have better written it. So for all inequalities, is written in this form. From left, 0 is smaller 0. Delta E from the right, 0 is larger 0. Delta E to the left, 0 is larger than 0. Delta E to the right, 0 is larger 0. And the same kind of applies for the second one. I can write on top of it, I think. Delta E from the left, 1 is larger than 0. Delta E from the right, 1 larger than 0. E to the left, but 1 electron is larger than 1, larger than 0. And delta E to the right, but 1 is larger than 0. And right, so the process happens in one direction because the delta E is smaller than 0 only for this and this one. Okay. All right. Now we can go to the third question. It's about writing the master equation. It's good to know that I think I made when I typed the presentation, I made a mistake that electrons in it flow from the right to the left, and why I did it, so I don't know. But the explanation is still valid. So let's introduce two probabilities, P0 and P1. These are the states of our system. So the system can be in the state where it doesn't have electron, it can have one electron, it have n electrons. We are interested only in these two states because the system is closed. So we cannot add more electrons in this particular column block, particular single electron transistor regime. So formally, we can write it in terms of two, right? So probability of zero state is decreasing when electrons enter from the right to the island, and it's increasing when they leave it from the island to the left. And similarly, the probability of state 1 is decreasing when the electron is leaving to the left reservoir, and increasing when the electron enters from the right. So it's simple, and we can solve it. But before we solve it, let's consider this gamma and the tunneling rates. And the tunneling rates are known from the following relations. We know if we have zero energy strip, that we don't have any voltage bias, for example, our tunnel rate would be 0. But in case we apply the voltage bias, we know that tunneling rate, which is expressed is current over E, and it is the current is given by G time conductance of the particular element or the lead or a junction over E, and it can be written in the following form: EV G over E square. And we know that this looks like delta E. So we know two limits of we don't know two limits, but we know that we can express gamma as function of delta E in the following form, and that's basically this formula, where delta E must be negative, because if it's positive, the process doesn't happen. We want to have the only processes where delta E is smaller than 0 are happening and are giving us a non-zero tunneling rate. So that can be written, and we previously obtained the gammas, the tunneling rates, obtained the delta E for the previously we used them for inequalities, but now we put it in this tunnel expression for tunnel rate, and that gives that gives us tunnel rates, and tunnel rates we can further plug in the master equation which we obtain. Dynamics. So now we are interested in the equilibrium current, and equilibrium current is something that when your probabilities of the states are not changing, but you still have, since the states are that you have 1 or 0 electron, in they might not change, but at the same time the tunneling rate guarantees that the current is flowing. So we don't that's the probabilities are not changing, doesn't mean that the current is not flowing. So that's kind of a thing. And to get these probabilities, we set time dependence to 0, and now we know that current can be expressed if we know that electron is on the island, then we know how fast it tunnels off that island into the right reservoir. So we say that current is E gamma from the right, with probability P0, or if we have electron in the island, it goes to the left with the tunneling rate gamma TL times its probability of being in the island. So we now just need to find the steady state probabilities, and that we can do with this way, with additional constraints. P0 plus P1 is 1, and that gives us the current. So I think this is final part of the exercise. Right. Let's now see. Do you have? Let's now ask questions, and I will try my best. Let's see. Let's have 4-minute break. We'll be back. So, I don't see any questions, so I assume that it was clear. Right. Let's now move slowly to the fourth exercise. It's actually it's a this exercise just made it more complex, not complicated, but it's good to practice these techniques on more than one exercise. I guess, yeah, in this exercise we are no longer going to draw column diamonds, but yeah. Right. So the system we have here is consisting of three tunnel junctions. This is this one, and two capacitors left here and here, and gate voltages can be modified as one wishes, and for a little bit of simplicity, we have a symmetric voltage bias, meaning that electrons are flowing from the right to the left. Yes, that's our current. And right, we know the electrostatic energy of the system to be in particular state, and we know tunneling rates, how to get tunneling rates from the energy difference. And yeah, so the first part of the equation is about master equations, and we shall write the system in the following way: that it's n1 comma n, that we represent the state of the system in this particular form. And the electron transfer is what we have said, that we are assuming single electron transfer where n1 and n2 must be either 0 or 1. So the states are 0, 0, 1, 0, 0, 1, 1, 1, and that's basically no 1. Yeah, 1. Yeah, 1, 1. Right. And yeah, and turns out we can have two processes. We can go from 0, 0 to 1, 0. The electron then hops in between the islands and move the island to the right. Yeah, moves the island to the right. And what can also happen is the electron starts the same way. It starts from 0, 0, it's 1, 0, but then it goes to 0, 1. But then another electron hops in the system before the electron leaves. The first electron leaves, and then the electron can leave in this particular fashion, and then it moves to this one. But yeah, then actually two options can happen. It goes to 0, or it can again go to the process here. So it's kind of a loop. Right. And now we want to write a system of equations. We have a following tunneling, correct? Which we need, and so let's write the master equation. We have this. We introduce the probabilities of a system being particular state, and then this we have this part. So if electron enters is at the state 0, 0, getting it to, and it moves to 1, 0, then the probability of 0, 0 is decreasing proportional to the probability that it is in the ground, that it's still say that. So, and the same, the electron goes from 0, 1 to 0, 0 if it moves to the right. So its proportion, its positive contribution to the probability of the state. So in P10, we can have electron which is the state P10, and it can there are 3 contributions. So two of them is that electron is already in this particular state, then it can decrease in a way that electron goes to the right island. But it can increase in 2 ways. It goes from 0, 0 and from 1, 1. And now we have this particular interesting thing is that if we let's evaluate the probability rate of 0, 1, then probability 0, 1 is can decrease in 2 ways. It can go to the state 0, 0, or we can have also that the electron is hopping to the left island and becoming state 1, 1. And yeah, and that's basically it. So this is what this is most yeah, just a catch in this exercise. And yeah, and this system gives us probabilities for the states to evolve. If we know the rates, the task. So this task is satisfied. We have written the equation in terms of right, and now we shall solve it in a steady state. To show it in a steady state, we say that all rates are 0 and are 0, and add additional equations that are the sum of probabilities is 0. So this is the system. We omit one of the equations because they are linearly dependent. And solve it. We saw it actually. Yeah, I used to do this on Blackboard. So these are 4 equations. This is 4 times 4 linear equation system, and perhaps let's say that the solution is follows from just algebraic manipulations, and focus on the third task. The third task is calculating the energy difference, which we will use for calculating the tunnel rate. And we know the expression for electrostatic energy. For example, we can calculate the E to 1, 0, which is electrostatic contribution. Electrostatic. And it's minus 2E squared over 3C. Yeah, it's just an algebraic formula. Plug it in, n is 1, 0, subtract it and collect it, and you get the nice form. Right, and then we can write full energy. So previously was electrostatic energies, and the full energies need to consider the work from the voltage source. So this is for electron going from state 1 to state 0, and we on the right we have voltage bias minus VT. So to put an electron which is negative already from the island to let's see if I'm correct. This was N1 and N2, I guess. From island 2 to island 1, we need to add and work. That means that delta E would be quite positive. The delta E LV over 2. On the opposite, if electron enters the system from the left, we can say it's E minus EV over 2. And if the transfer is happening between them, there is now work done by voltage source on the voltage source, and delta E11 to 10 is, again, we need to do a work on putting negative electron to already negative voltage source. So this system is energetically consuming. From 0, 1 to 1, 1. Now we can add electron from the left and get some additional boost. Right. So these are the energy differences. Now we can use them to express rates. And previously I did made an error, so we need to minus EV t plus EV over 2. Was this inside one was nothing, plus EV over 2 and minus EV over 2. And right, so this gives us rates. And yeah, and this is a task 4. Last task is to calculate the current. And the current, the best way to say what the current is consider the process in between when the electron goes from the left to the right. If one considers a different process, one also sometimes needs to consider multiple contributions to the current. So it's usually it's best to consider the state which does have only single contribution. So that the current is kind of obvious. In this case, is that electron from the left island goes to the right island with the tunneling rate gamma 1 0 to 0 1. And now we just need to find the steady state probabilities, which are also called equilibrium probabilities. And for that, we would need to solve the system in the task 2, and this would give us the following. And in this current expression for current, we could substitute the rates which we obtain at the task 4, and that would give us the answer to the last task of this exercise. So I wonder if anyone is still here. You may ask questions. Right. Do you have any questions about any exercise on this particular set? Perhaps P10. P10. Can you say me which page it was? P10. Are you referring to this particular? Or P10. We use P10. So we use this one here, right? But to get this P10, one solves this particular system, and it is right here. But since it's algebraically involved, yeah, I usually don't do it. Okay. More questions? I can go to an exercise in the set.
All right, so if there are no more questions, let us round up the sessions. Any questions about course in general, about exams, about anything? Also doesn't seem to be the case, so there are no questions. Let us meet next Friday. I have already posted a Zoom link, if I'm not mistaken. So, see you on Friday. Bye.
Bye.
Thank you, Yanis.
So, yeah.
Thank you.